Hello. This video includes information on quantitative analysis. Specifically, we're going to talk about titrations, gravimetric analysis, and combustion analysis. And essentially, what we're doing when we deal with quantitative analysis is we're determining the amount or the concentration of an unknown, looking at different kinds of reactions. And in order for us to do this, we have to know what the reaction is. We have to know what the balanced equation is, so that we can do appropriate stoichiometry with the information. And there are three different types of quantitative analysis problems that are listed here. We're actually only going to go through two of them just for time purposes. So the first one is called a titration. And a titration is a type of quantitative analysis in which the concentration of a solution is determined by a reaction with either a known concentration of another solution or with a pure solid of an unknown mass. Okay, gravimetric analysis is a type of quantitative analysis in which we want to deal with the concentration of a particular compound by producing a precipitate and measuring the mass of that precipitate. And the third type is called a combustion analysis type of a problem. And that's where we would combust some kind of hydrocarbon, collect the carbon dioxide that was produced, and collect the water that was produced, and do a stoichiometry problem to determine the empirical formula of that hydrocarbon. We're not going to go through the combustion analysis. It's a very long, it's not super hard, but it's a super long type of a problem. And just for time purposes, we're going to talk about titration, and we're going to talk about gravimetric analysis, and we're going to kind of skip the combustion analysis. So let's look at titrations first. So here's a sample question. It says an aqueous solution of nitric acid is standardized by titration of 0.114 molar barium hydroxide. If 12.3 milliliters of the base, the barium hydroxide, are required to neutralize 11.4 milliliters of the acid, the nitric acid, what's the molarity of the nitric acid? So this is kind of the way this setup for a titration goes. Okay, we take a flask and we put the unknown solution in here. So the acid is in here. This is called a burette that can measure volumes of liquids pretty precisely. And we put the base of known concentration in here. And then we drain the base into the acid. The neutralization reaction takes place. We usually put some kind of an indicator in here that changes colors when the reaction's complete. And then we can measure the volume of the base that was needed to completely neutralize the acid. And if we know the molarity and the volume of the base, we can figure out the moles of the base. And if we know the moles of the base in the stoichiometry, we can figure out the moles of the acid. And if we know the moles of the acid and the volume of the acid, we can figure out its molarity. So that's the concept. So here's our reaction. Okay, nitric acid is HNO3. Barium hydroxide is BaOH2. It's a double displacement reaction. It's a non-redox reaction, and it's an acid-base reaction. We're going to produce barium nitrate, BaNO3, 2, and water. And the stoichiometry is 2 to 1 to 1 to 2. All right, so the first thing we're going to do is we want to figure out how many moles of acid there are in the unknown. Okay, well, how do we do that? We know the volume of the base, and we know the molarity of the base. If we take the volume times the molarity, that's going to give us the moles of the base. And if we know the moles of the base and we have the balanced equation, we know what the mole ratio is from base to acid. In this case, it's a 1 to 2 ratio. So we can figure out the moles of acid. So we have 0.00282 moles of acid in our unknown. The volume of the unknown is 11.4 milliliters. We can calculate the molarity. Okay, we know molarity is moles per liter. So we would take 0.00282 moles, divide it by 0.0114 liters, and we can calculate what the molarity of that unknown acid is. That's the concept behind a titration problem. It's really just knowing what molarity is and knowing that a balanced equation is a mole ratio. It's kind of combining different things together. So let's look at another problem. Okay, a little bit different this time, because instead of having a solution and titrating it, we're going to use a solid. The concept is essentially the same. So a 0.300 gram sample of, this would be sodium oxalate, is dissolved in water and titrated with, this is potassium permanganate. If it takes 46.8 milliliters of potassium permanganate for the reaction to go to completion, what's the molarity of the potassium permanganate? Well, molarity is moles per liter. We know the volume of the solution. We have to figure out the moles of the solution, or the moles of the potassium nitrate, the solute. Well, we know the grams of the substance that we're titrating. We can figure out the moles. And if we know the balanced equation, we know the stoichiometry. So that's the thought process for this problem. Again, we'd have the same kind of setup. Okay, we'd put our solution that we don't know the molarity for in our burette. We'd put the sodium oxalate into a flask and add some water to it, and then titrate it until we get to the end point, or until the reaction is complete. Okay, now here's the reaction. It's already balanced for us. We don't really have to worry about that. The important part is it's 2 moles of sodium oxalate for every, 5 moles of sodium oxalate for every 2 moles of potassium permanganate. That's the ratio we're going to be using in the problem. So we would take the grams of sodium oxalate and convert it to moles. We can go from moles of sodium oxalate to moles of potassium permanganate. And then once we know the moles of potassium permanganate, we can figure out the molarity of the solution. All right, so we kind of write down underneath what we're given, just makes it a little easier. So we have 0.300 grams of our sodium oxalate and 46.8 milliliters of our unknown solution. All right, let's take the 0.300 grams of sodium oxalate and first convert it to moles. Okay, well, we'd look up Na2C2O4 on the periodic table and we'd figure out the molar mass. We're at moles of sodium oxalate. It's a 5:2 ratio based on the balanced equation. So there must be 8.96 times 10 to the minus 4 moles of potassium permanganate in this solution. Now that we know the moles, we can figure out the molarity. So we take the moles of the potassium permanganate, 8.96 times 10 to the minus 4, divide it by the volume, but keep in mind it needs to be in liters. It's moles per liter for molarity. This was in milliliters. We divide it by 1,000. We get 1.91 times 10 to the minus 2 for the molarity of this unknown solution. So titrations can be done where we have 2 solutions and we know the concentration of one of the solutions and we can figure out the concentration of the other solution. Or it can be used with a solid and an unknown solution, and we can figure out the concentration of the unknown solution. Okay, it's really just an applied stoichiometry problem. So I'm going to give you a problem to do on your own. And then after you do that problem, maybe we'll take just a couple-minute break and come back. So it says titration of 20.0 milliliters of an acid rain sample requires 1.7 milliliters of 0.01811 molar sodium hydroxide to reach its endpoint. Okay, that just means that the neutralization has taken place. If we assume that the acidity of the acid rain is due to the presence of sulfuric acid, so that's going to be our acid, what was the concentration of the sulfuric acid in that acid rain? Okay, well, the first thing we need is a balanced equation. So we have sulfuric acid and sodium hydroxide reacting together. Okay, so there's our reaction. Sodium hydroxide is NaOH. Sulfuric acid has sulfate in it, so H2SO4. Okay, it's a neutralization reaction. It's a double displacement reaction. It's a non-redox reaction. All different ways that we can kind of describe this acid-base reaction. We're going to produce sodium sulfate and we're going to produce water. So we know the volume and the molarity of the sodium hydroxide. That means we can figure out the moles. We know the stoichiometry because we know the mole ratio here is 2:1, so we can find out the moles of sulfuric acid. And once we know the moles of the sulfuric acid, and we know the volume of the solution it was in, we can figure out the molarity of the sulfuric acid in that acid rain. Okay, parallels the problem, the first problem we did where it was a solution in an unknown solution. See if you can figure this one out. All right, so let's see how we did. So if we take the 1.7 milliliters of sodium hydroxide and convert that to liters, you don't necessarily have to show this step. And then we take the volume and multiply it by the molarity. That'll give us the moles of sodium hydroxide. It's a 2:1 mole ratio to get to sulfuric acid. So we have 6.89 times 10 to the minus 5 moles of sulfuric acid. Okay, we want the molarity. So that would be the moles divided by the 20 milliliter sample. So 6.89 times 10 to the minus 5 moles of sulfuric acid in the 20 milliliters or 0.0200 liters would give us 3.4 times 10 to the minus 3 molar sulfuric acid. And significant digit wise, okay, since there is 1 or 2 significant digits in 1.7, we're just carrying an extra significant digit here. This really should be 6.9 times 10 to the minus 5 if we wanted to round it off, but we'll just carry an extra significant digit in our math, and then we'll round it off when we're done. All right, my friends, let's get started with the last thing we're going to do in this chapter. So we are going to talk a little bit about gravimetric analysis. It's just another type of quantitative analysis, but it's really just an application of stoichiometry. Okay, so in this case, what we would be looking at is some kind of a solution, and we add another solution or we add a solid, and it precipitates what's dissolved in the solution. And we can use stoichiometry to figure things out. So in this case, it says how many grams of lead bromide will precipitate when excess magnesium bromide is added to 66.0 milliliters of 0.539 molar lead nitrate. All right, so think about this. Here's the reaction. It's already balanced, so it's a 1:1:1:1 ratio. Makes maybe it a little bit easier. But what are we given? Well, we're given the volume and the molarity of the lead nitrate. So in our heads, we say to ourselves, well, if I know the volume and I know the molarity, I can figure out the moles. Well, if I know the moles of lead nitrate and I have excess magnesium bromide, that just means all the lead nitrate reacts. So if I know how much lead nitrate reacts, I can use my stoichiometry to find out how much lead bromide is going to precipitate. It's an applied stoichiometry problem. So we would take, oh, here's just a picture of it. So we would take the molarity times the volume of the lead nitrate, and that would give us the moles of the lead nitrate. And then we take the moles of the lead nitrate, and it's a 1-to-1 ratio. And then we go from moles of lead bromide to grams of lead bromide. This comes off the periodic table. And that'll tell us how much lead bromide would precipitate out of the solution. And what this is just showing us is we take the solution that has the lead bromide solid in it, and we just put it into this filter paper, and essentially gravity causes the solution to go through the filter paper and the precipitate gets stuck in the filter paper. Okay, that's why it's called gravimetric analysis. But it's essentially a stoichiometry problem. If you know the molarity and you know the volume of something, you can figure out its moles. If you know the moles and you know the stoichiometry, you can figure out another part of the reaction, and then you can figure out the grams. Okay, so let's do another one. Calculate the number of milliliters of 0.412 molar potassium hydroxide required to precipitate all of the iron ions in a 155 milliliters of 0.555 molar iron iodide solution as iron hydroxide. Okay, so here's the reaction. Okay, we have a solution of iron iodide. And we know the molarity and the volume of the iron iodide. That means we can figure out the moles. We know the molarity of the potassium hydroxide. We want to find out the moles of the potassium hydroxide to completely react. So that means if we can figure out the moles of the iron iodide, we can figure out the moles of the potassium hydroxide. And if we know the moles of the potassium hydroxide and the molarity of the potassium hydroxide, we can figure out the milliliters. So again, we spent that time talking about what molarity is, and this is just combining it with some stoichiometry. Okay, so first figure out your moles of iron iodide. That means you're going to take the molarity times the volume. Okay, once you do that, it's a 1-to-3 ratio to get your moles of potassium hydroxide. And then once you know the potassium hydroxide and you know the molarity, you can figure out the milliliters. All right, so if we take 0.555 moles per liter, remember that's what molarity means, and we multiply it by the volume, this essentially gives us the moles of the iron 3 chloride. It's a 1-to-3 ratio to get to the potassium hydroxide, so we know the moles of the potassium hydroxide. Okay, well, we want to find the volume. We know the moles, we know the molarity. To calculate the volume, okay, we would take the moles and divide it by the molarity. So 0.258 moles of potassium hydroxide divided by the 0.412 molar solution. So we would need to add 646 milliliters of the potassium hydroxide solution to our iron iodide solution in order to precipitate all of the iron out of the solution as iron hydroxide.